In 1991, during the Gulf War, U.S. pilots began reporting something unusual. A damaged aircraft returned to base with one engine destroyed, half a tail missing, and hundreds of bullet holes. The aircraft still landed safely. From an engineering perspective, this should not happen. Modern combat aircraft rely on speed, altitude, and stealth to survive. They avoid being hit. But the Fairchild Republic A-10 Thunderbolt II does the exact opposite. It deliberately flies low, slow, and directly over the battlefield. That means it must survive a physics problem that most aircraft designers try to avoid entirely. Projectile density. In a modern battlefield, a low-flying aircraft enters a zone filled with heavy machine guns, anti-aircraft cannons, shoulder-launched missiles. Statistically speaking, something will hit the aircraft. So the real engineering challenge isn't avoiding damage. It's designing an aircraft that keeps flying after being shot. And that requirement completely changed how the A-10 was engineered. The A-10 was built for one specific mission: close air support. That means protecting troops on the ground. The problem became obvious during the Vietnam War. High-speed jets like the F-4 Phantom II could deliver bombs. But they had a physics limitation. They were too fast to aim accurately. At 900 kilometers per hour, a pilot has only seconds to identify a target. If the aircraft misses its attack run, it must fly several kilometers away just to turn around. Ground forces needed something very different. Long loiter time, extreme accuracy, ability to fly low and slow. But this creates the central engineering problem. Low altitude means maximum exposure to enemy fire, and the probability of survival drops dramatically. To understand why the A-10 flies low, we need to look at basic ballistic physics. Visual, projectile trajectory diagram. When a projectile leaves a gun, gravity immediately starts pulling it downward. The vertical drop is determined by a simple equation. Drop equals 1/2 gt superscript 2, where t is time of flight. Now imagine firing a cannon from 1,000 meters altitude. The projectile might take 2 seconds to reach the ground. That allows wind, target movement, and aiming error to dramatically increase the miss distance. But at 150 meters altitude, the time of flight drops drastically. That means far higher accuracy. This is why close air support aircraft must operate close to the battlefield. But once you fly that low, you enter the lethal range of nearly every weapon on the ground. And that's why the A-10 had to be engineered like a flying armored vehicle. Most aircraft are designed around the engine. The A-10 was designed around its weapon, the GAU-8 Avenger cannon. Visual, exploded view of GAU-8 rotary cannon. This weapon fires 30 mm armor-piercing rounds at nearly 3,900 rounds per minute. Each projectile weighs roughly 400 grams and exits the barrel at over 1,000 meters per second. Using kinetic energy calculations, 1/2 MV superscript 2. Each round carries about 200,000 joules of energy. That's roughly the energy of a 1-ton car hitting a wall at 70 kilometers per hour. And the cannon fires 65 rounds every second. This allows the A-10 to destroy armored vehicles with short bursts. But the gun introduces a serious engineering problem: recoil. When the cannon fires, it generates about 45 kilonewtons of force. That's comparable to the thrust of a small jet engine. If mounted improperly, the recoil could literally push the aircraft off target. So engineers did something unusual. They aligned the cannon perfectly with the aircraft's centerline. Visual, front view showing offset landing gear. The nose landing gear is slightly offset to the side because the gun occupies the center. Even the pilot's seat is aligned with the cannon's axis so the recoil forces travel directly through the aircraft structure. This minimizes rotational torque and keeps the aircraft stable while firing. But recoil was only one of many survivability problems. If the A-10 is going to fly through gunfire, it needs armor. The cockpit is surrounded by a 540-kilogram titanium shell. Visual, cutaway animation showing titanium cockpit armor. Engineers call this the titanium bathtub. It protects the pilot from 23mm anti-aircraft shells, armor-piercing rounds, fragmentation. But armor alone doesn't solve the survivability problem. Aircraft usually fail when systems fail. Hydraulic lines rupture. Control surfaces stop responding. To prevent this, the A-10 uses multiple redundant systems. It has 2 independent hydraulic systems, backup manual flight controls, duplicated avionics. Even if the hydraulics fail completely, the pilot can still fly using manual cable controls. This is extremely rare in modern jets, but it allows the aircraft to survive catastrophic damage. Look at the A-10 and you'll notice something odd. The engines sit above the fuselage. Visual, side profile highlighting engine placement. This unusual design solves several battlefield problems. First, foreign object damage. Close air support aircraft often operate from rough airstrips. Debris can be sucked into engines. High-mounted engines reduce this risk. Second, infrared signature. Missiles often trap heat from engine exhaust. The A-10's engines are partially shielded by the tail structure, reducing heat visibility from below. Third, battle damage isolation. The engines are widely spaced apart. This means a single missile is unlikely to destroy both engines simultaneously. Once again, survivability is achieved through geometry and redundancy. All of these design decisions come with compromises. The A-10 is slow. Maximum speed is about 706 kilometers per hour. Compare that to modern fighters like the F-35 Lightning II, which can exceed 1,900 kilometers per hour. The aircraft also has a large radar cross-section. It is not stealthy. This means it cannot safely operate in airspace defended by advanced missile systems like the S-400 missile system. In modern warfare, the A-10 must wait until enemy air defenses are suppressed. Only then can it safely enter the battlefield. But once that happens, few aircraft are better at supporting troops on the ground. During the Iraq War in 2003, A-10 aircraft flew hundreds of close air support missions. They destroyed tanks, artillery, armored vehicles. Ground troops quickly learned to recognize a sound. Not the cannon itself, but the famous BRRT. Visual, slow motion footage of GAU-8 firing. The aircraft flies faster than the sound of the rounds. So by the time soldiers hear the cannon, the target has already been hit. This combination of precision, survivability, and sustained firepower made the A-10 one of the most feared aircraft in the conflict. From an engineering standpoint, the A-10 is almost the opposite of modern fighter design. Instead of stealth, it uses armor. Instead of speed, it uses ballistic precision. Instead of avoiding damage, it is built to absorb it. But warfare is changing. Modern integrated air defense systems are becoming more sophisticated. Aircraft like the F-35 Lightning II can perform multiple roles while remaining survivable in heavily defended airspace. Maintaining a specialized aircraft like the A-10 is expensive for a mission that may be shrinking. Yet decades after its introduction, soldiers still request it by name. Because sometimes the best engineering solution isn't the most advanced machine. It's the one designed around the fundamental physics of the problem. And in close air support, those laws still favor a flying gun.